Let's talk now about changing bases. Why do we talk about this idea? It's because we've said that matrices are a representation of operators on a vector space. But the matrix itself that represents the operator depends on the choice of bases. And given that choice, that some of you may choose different bases, if we want to compare our results, we need to know how the matrix representation of the operator changes as we change the bases. So this is pretty important and very useful. And it also shows, as we will see developing these ideas, that there's some information in the matrix representation that is in fact independent of the basis that you choose to represent the operator. So let's begin by saying that the matrix representation, REP, of an operator T that is a linear operator on V depends on the chosen basis V1, V2 up to Vn on V. And indeed, you've seen this formula already several times that we say T on Vj is equal to the sum over I of Tij times this vector is Vi. And now that I want to emphasize the basis dependence, I put Tij of V. Because this result, these numbers, depends on the fact that we've chosen the vectors V as our basis. So these are numbers. And that depend on the basis V. So what we want to deal with now is the possibility that you have two bases. Basis 1 made up of vectors V1, V2 up to Vn, and basis 2 with basis vectors U1, U2 up to Un. And we will have two operators. One operator A that takes these basis vectors to the second set of basis vectors, and an operator B that does the reverse. So actually we write this as follows. We say that if you act with A on Vk, you get the vector uk. That's the expression that this arrow pushes any vector v to the corresponding vector u. A on vk is uk. Similarly, vk would be equal to b uk. And this is true for k equal 1 up to n. These operators A and B are linear operators, and they're basis changing operators. You see, this relation, you should think of it as a relation between vectors, an absolute relation. These are not components, these k symbols. This is saying, say, the third basis vector is taken by A into the third basis vector of the second basis. And therefore, for example, you can have the following situation. You can calculate what is B times A on Vk. Now, A on Vk is uk, so you have B uk, and B uk is back to Vk. So BA acting on Vk is Vk. So since the V's form a basis, and this is true for every k, BA doesn't change any vector. So BA is the identity vector. Similarly, you could say AB is the identity matrix, I'm sorry. AB on UK, B on UK is VK, so this is A VK, and A on VK is UK, so again, AB is a matrix that doesn't do anything. It's an operator, in fact, that doesn't do anything and leaves vectors fixed, unchanged. So it does that because it does so for every basis vector in a basis. So what we've learned is that AB is equal to BA is equal to the identity. A and B are inverses of each other. A and B are inverses of each other. And this should not be surprising. You had it from the beginning that A pushes you down, B pushes you up. So that should have been the case. Now, what is the main goal of our discussion now? Our real objective is to see how our Tij of V, the matrix elements of this operator in the V basis, related to Tij that will be computed with the second basis, the U basis. So this is our main question. This is the question that we want to answer. But before answering this question, first a claim. An important claim that this, unless you do it, things are a little confusing. So claim. I claim that the matrix representations of A and B, so when you try to think of A and B as matrices, you could say, okay, well, I'm going to think of them, they're linear operators, as matrices. So which basis should I use to think of them as matrices? And the wonderful thing is that it doesn't matter. The matrix representations of these operators, because they are basis-changing operators, the matrix representations agree in both bases. So the claim is that the matrix representation of A, also on B, is the same in the V and U basis. So let's write this. Suppose you were computing A acting on VK. Well, you would say, all right, this is the sum over I, A, I, K. I'm using the V basis, so it's this times VI. On the other hand, if you had AUK, you're acting on the U vector, so we could write it as a U superposition using the AIK in the U basis, UI. So we want to show these two numbers are the same. And a strategy to do that is to rethink of this equation again in a slightly different way. So think of AUK. And what is UK? Write it as AVK, because we want to get something of this form, but express it in terms of the V operator. So UK is AVK. And now use the defining action here. So you have A on sum over I, AIK of V times VI. Now you have this other operator, A, and it's going to go in. It's acting on a sum of numbers times vectors, so it hits on the vectors. So what does it give you? It gives you the sum of numbers, ik of v, times a times vi, but a times vi is ui. And there we have it. So I'll indicate that by saying that this has gone and acted on that vector and given you a ui. But now you can simply compare and say, well, a on uk is this, and it's equal to this. But these are exactly the same expressions, the same vectors, so the components must be exactly the same. These are, after all, basis vectors. So you've shown that aik of u and aik of v are the same. So indeed, that was our claim. So we have learned that aik of v is equal to aik of u, and therefore we don't really need to specify which set of basis vectors we're using to describe this operator as a matrix, so we just simply call it aik. And the same for b. So these are nice relationships. We'll box them. And on the same spirit, since we have that a and b are inverses of each other, we would write that bij ajk is equal to delta ik when you sum over j. That's the matrix product, and saying that they're inverses of each other, they multiply into the unit matrix or a Kronecker delta. And we don't need to say again whether we use the u or v basis. Both b and a are basis independent among these two choices. And similarly, that's equal to a times b, so a ij b j k. They're matrix inverses of each other. So we have all the preliminary things that we need in order to answer the question, our main question: how are these two matrix representations related? So let's do it now.